Morning, everyone. Good to see we've got a good turn-up after last night. I was a little bit concerned when I left to still see so many people still in the bar, but good to see you all this morning. So this is our final keynote talk for the conference. I should say that all of the keynote presentations that we've had here at the conference have been recorded, and they will be going up onto the OCNS, we've got to work out exactly where, but they'll be going up on the OCNS channel. I think there's a YouTube channel that already exists, but keep your eye out, and if you want to let anyone know about those, they will be available over the coming week or so. So we're very glad to have Tara Hamilton today to give our fourth and final keynote talk for the conference. Tara is currently a principal scientist at Kuvos, which is an edge AI neuromorphic technology startup. So prior to this, Tara was an associate professor at the University of Technology in Sydney, where she still holds an adjunct appointment. She's also the co-founder of RF Perception, which is a startup focused on personal radar with applications to vital sign detection. And before starting her academic career, Tara worked for Cochlear Limited, which is the bionic ear or cochlear implant manufacturing company based here in Australia, and at G2 Microsystems, a chip design company. So Tara has a fantastic academic record. She's published over 120 academic papers and has 4 patents. During her academic career, she's received over $3 million in research funding. And her research interests include neuromorphic engineering, integrated circuit design, embedded systems, machine learning, wearable and implanted devices. And she also mentions that in her spare time, I don't know how much spare time she actually has, but Tara enjoys playing Lego with her 6.5-year-old twin boys, growing vegetables and carnivorous plants in her, what she says is often all too neglected garden, and swimming. So it's a delight to have you, Tara, and we look forward to your presentation. Thank you.
Hi everyone, I'm extremely excited to be here today, and thank you for overcoming your hangovers to make it. I'll try to keep it exciting so that nobody falls asleep. I was told how to use all this and now I'm getting all confused, but we'll see how I go. Whoops. Okay, so yeah, as Tony said, I have a lot of history in neurotech and neuromorphic. For 23 years, I counted. I feel so old now. And 18 of those years was spent in academia, where I'm still adjunct at UTS. In that time, I've tried to keep really close to industry and working a lot with industry, so it's been very applied, my career. A few years back, I did the leap into startup land, which was interesting and fun. And now I've sort of jumped out of university altogether and am a principal scientist for a tech startup. Here we go. So what I'm going to talk about today is how to take neuroscience and all the stuff that you have been exploring in your research and making it into cool technology. As I said, I've been really focused on applied during my career, and it kind of started early. When I worked for Cochlear, I was there for 5 years, and we worked on the totally implantable cochlear implant, and already I could see, wow, it's really hard to interface with the body. You know, like you can make the coolest chip and have the coolest processor, but actually connecting to the body, actually making neurons fire, it's inefficient, it's very imprecise, it's very clunky. And so, you know, I sort of became obsessed with that idea, and it's been a little bit of an obsession of mine for, well, 20 years now. And so that led me down the path of doing a PhD, which was more focused on, you know, stuff that I could manage, like modeling. And so in my PhD, I did models of the cochlea, so computational models, but actually implementing them in silicon. And then that brought up a whole heap of new problems, like noise absolutely kills your model. Things like power consumption, like when we're copying or mimicking biology, we're supposed to that's the goal, right? To reduce power, because we've got these awesome nervous systems that work on almost no power. And yet, when you build these things, you need a lot of power to make them work. And so, again, new obsessions, how to deal with noise, how to deal with power. And then for the back end of my academic career, I was really focused on algorithms that might overcome some of these problems. So instead of fighting the noise, could the noise be used to facilitate computation? Are there ways to do things like machine learning better than statistical approaches that don't require so much power? And so these are kind of all clumped into the back end of my career. Better algorithms that work with noise, better ways of doing things in hardware, how to reduce power, and this is still kind of what I work on now. And I guess the sundries is that, during looking at neuromorphic particularly, and algorithms particularly, I've also done a lot of work with deep brain stimulation, nerve regeneration and wearable devices. And again, all those are kind of similar. They all have the same problems with power consumption, with where to connect, how to connect. And then looking at RF electronics, looking at 5G circuits and things, which isn't really related here, but it's also power and all sorts of annoying problems that come when you're trying to build something. And then, as Tony said, my startup looks at radar and vital sign monitoring, which again is about dealing with human bodies and all the imperfections that come with it. So this is kind of where I come from in what I'm looking at. And how do I take all this and inspiration from all the great talks that I've heard here today, and how do you use that to make better technologies? Now, I've heard lots of people say that they want to make a brain, and that's not here, but people, neuromorphic types, and that's great. It'd be great to make a brain, but I feel like we can probably take inspiration from little bits of what we know about neuroscience and actually make technologies that are immediately useful, immediately have benefits to improving our ability to do robust machine learning or low power devices. And so that's more my bent. Never tried to build a brain. I don't know that I'll live to see anyone understand how it all works. And certainly here we see there's so many levels to the understanding, from intricate single neuron models and how enormously complicated they are to large scale models, everything in between. There's just so much to learn. So all you can really do is make some inferences and perhaps apply that to make a technology that can do something just a little bit better. One of the issues when you're trying to make a widget from neuroscience is that it's such a broad field. There's so many niches, and often you can see similarities, and I'm sure when you're watching other talks, you're like, oh, that's kind of similar to something I'm studying, even though it's quite removed. But it is so broad, and it's hard to keep track of everything that everyone's doing, and no one can do that. So that's one of the problems. It's also nice because it makes it interesting to come to conferences like this. The capabilities of what we have in technology at the moment, like we've got awesome computers, but they're really bad at doing parallel computation. They're really bad at the kind of things that we know the body does. So I'm going to go into that a little bit later, but computers were designed by humans, and humans like to understand what they're looking at, and so the whole thing has been designed, and so it's understandable, but it makes it difficult to then implement on top of that the quite complicated aspects of how a neuron works or the dynamics of how a simple neural circuit operates. So then there's also the issue of establishing collaborative opportunities between people that want to make technology and people that do the science. So over the years, many times I've tried to have collaborations with quite basic science people. And, you know, it works for a little while, but there's such a disconnect between what the goals are. And it's kind of a shame. It makes sense. I don't know how to make that work. But in terms of moving forward with technology development, there hopefully has to be some marrying of basic science with development. And then, of course, there's always so much we don't know. And I'm going to fully admit, as an engineer, we often just go, oh, this I can do, and then we just race off in that direction and we just make something. So these are the issues that we have to deal with when we're trying to put together, you know, technology from neuroscience. So why do we want to do this? Mostly because there's sort of demand. We're kind of moving towards this autonomous world where we have sensors everywhere. We kind of already do. We've seen sort of Tesla cars take out pedestrians when they didn't see something they didn't understand. This is an absolutely huge problem. These car manufacturers and tech gurus, they're going to go ahead and build this technology. And so it's kind of the responsible thing to try to make it better so that we don't randomly kill people because, you know, the AI didn't understand a stop sign in a different context. Of course, things like medical interventions. So there's been a few talks about closed loop. And closed loop is super exciting. So it has an opportunity to actually do targeted stimulation, targeted measurement, and reduce power consumption, and actually provide the kind of intervention for the patient that's needed at a timely point. If we have better learning technologies, then these kind of medicines and these kind of interventions can be more personalized. We've seen some data from clinical trials during this conference, and there's such variability between individuals, and because we don't understand the brain that much. If we have better algorithms that are able to learn an individual's response to a stimulation, then we can have safer devices. And so I think that's a really big goal for us in sort of medical devices industries. And then, of course, there's the usual kind of monitoring and defense applications, which aren't necessarily that interesting, but obviously there's a lot of money out there, and so, you know, we can't pretend otherwise. So I'm going to talk about, given all that introduction, which was quite long, I'm going to talk about some of the issues in translation from taking some neuroscience concepts to developing technology. And so through all the sort of adventures that I've had, sort of four things which are constantly, you know, I have to kind of come up against when looking at what's in the neuroscience literature and what can I actually build with current technology. So one of those is connectivity. I've kind of already discussed it. It was a very early realization of mine. You know, cochlear implants, electrode leads, things are amazing how they work, and I think it's like, you know, how awesome is the brain? But it seems like, you know, we should be able to do better, or maybe we can't, I don't know. In terms of artificial networks, there's the other problem of connectivity with, if I take a single neuron, like a proper one out of your brain, it's got so many connections going all over the place, many dendrites. It's a difficult thing to understand. And mostly nobody really totally fully understands it. We've got models, but we're always simplifying. If I want to build a neural circuit, which bits should I abstract away? Which are the important bits? How do I create enough connections so that that circuit behaves like the actual neural circuit? And what is the right thing to abstract? So connectivity in two contexts, one being how to connect with the body, the other being how to create models that don't perfectly replicate or mimic the biological analog, but that have enough of the properties to be useful. The other thing is non-linearities. We've kind of seen, we all kind of linearize everything because the maths are easier. But we can see that the nonlinear response of sensors and neurons actually are the things that make those systems work properly. And often they're completely abstracted away because they're difficult to deal with. So how much of the nonlinearities do we need to include? How much can we just approximate away with sort of linear models? And in doing all that, if you keep the nonlinearities in your model, how do you keep your model stable? And these are huge problems when you're trying to build a computational model and then go to a physical model. These are extremely difficult to deal with. And then there's the kind of thing that I just say complexity, the big fuzzy bear that's like everything is complex. We've got a system with lots of moving parts, feedback, feed forward, connecting to everyone. It's difficult to just cut out a part of the brain and say, I'm going to make a model of this part without sort of thinking, well, it's probably completely interconnected with everything else, and how do I even try to abstract this away? How to understand it all and how to understand which bits aren't necessarily needed to make the system work. And then, of course, there's the kind of, usual engineers completely obsessed with power, not with dictatorial power, but, actual electrons moving in wires. So when we're talking about connectivity, why do we have so much connectivity? I'm sure everybody in this room has their own answer. I don't think I'm being too controversial to say that the part of the reason we have so much connectivity is because the brain's doing predictions a lot. So it needs to have, constant inputs and outputs throughout its network. We have a lot of senses. We rely on our eyes and our ears and touch and smell, and these senses need to give us sort of as higher fidelity information as possible, and that information needs to be, distributed quickly. So lots of connections means that things can move around faster. And then, of course, as an engineer, the brain is so slow. Its clock is sort of in the kilohertz. Whereas, your phone has probably got a gigahertz clock or something like that. So the brain is like a little snail, but somehow it gets through that by just doing everything in parallel. And that's possibly an answer to how we solve these problems, I'm not sure. But, from an engineer's point of view, there's not much I can do about connectivity with the current technology I have. So probably a lot of you haven't seen what an integrated circuit looks like, but it's very planar. You have layers, but only about 6, in a typical chip. You can never create the kind of connectivity of a single neuron, let alone a whole network of neurons. And so this is something that we can't do a complete analog, right? We can't take somebody's, topological map of a neural circuit and create it exactly in a chip, because it just cannot happen. And please prove me wrong if you've done that. There are other technologies coming about, so things like atomic switch networks, which are kind of cool material science things that have interesting properties and kind of look like neural connectivity. It remains to be seen whether or not that kind of technology will become mature enough to be able to use it to create brain circuits, but at the moment this is not something that currently exists. So what we usually do we use the fact that the brain is super slow, and we usually do something called time multiplexing, where we can have billions of neurons in our chips, and we just solve each neuron in a fraction of a time step, and then put all the results together so that on the outside it looks like real time. It looks like the speed of an actual brain circuit. There's a lot of problems with this, but this is sort of how technology has solved the connectivity conundrum. And obviously, whether we come up with something better, and whether that's from new technology or maybe from better understanding of neural networks and what parts of the connections are needed and what aren't, I'm just not sure. In terms of the problem with physical connections with the brain, this is more of just an aside, but yesterday I think we saw some evoked potential responses from deep brain stimulation. And so this is similar to that. This is for Parkinson's disease. But in this study, when we stimulated the brain, you get this enormous evoked potential that kind of just swamps out everything. And we were looking for late responses, and these are several orders of magnitude smaller than the evoked potential. And so when you're trying to actually find these biomarkers, because you've got such primitive connection with the brain, I'm saying primitive, but we're all very advanced. It's an electrode lead with 4 electrodes, and you're stimulating on one, and you're trying to find a signal on another one. You need pretty sophisticated electronics in order to be able to even sense a signal, and it's easily missed, and noise can overwhelm you. And if things aren't, slightly shifted in place, then you may not catch it. And these are some of the issues with creating closed loop DBS, because the response is so variable and it's so hard to find. So, yeah, I promise no answers to any of these conundrums, but connectivity in terms of how to build connections of real networks, and connectivity in terms of how to connect to the brain, these are problems that really need to be overcome in order to create better neurotechnologies. I hope some people appreciate the pun here, but it's fine if you don't. So non-linearities, I feel like are kind of, it's kind of, nobody really wants to talk about them because they're too hard. But we see it all the time. There was a talk on Sunday, I think, looking at photoreceptor cells, and clearly the dynamic range of those cells is improved by some sort of compressive non-linearity, something like this. And so that seems to be found all over the place. Even neurons do it. It's obviously a way to keep a signal within a particular range, and it has these benefits of improving signal to noise. This sort of nonlinearity requires feedback. You need to know the intensity of the signal that's coming in order to change your response. And because of the sort of maths that sort of govern these kind of nonlinearities, you need some sort of way to stop getting into an unstable point where everything just goes to hell. So these are kind of, if you want to have a system that really mimics the biological system, then you need to include nonlinearities, or at least some sort of approximation of those. And later today, I think we're going to see some talks about criticality in the brain. And so I'm going to give a completely wrong description of that now. But the idea is that there's kind of these states where, so this was with matter and temperature. So in a sort of cooler temperature, the matter kind of creates very structured kind of behavior. If the temperature's too hot, then it's sort of all just, it's random. And somewhere in between, some critical temperature, you get sort of the maximum pattern memory capacity of the system. And this is sort of where you want your systems to operate, because this is where they have the most ability to be able to learn and respond in a way which improves your signal performance. So when we're looking at the cochlea, and I'm pretty sure that this would be similar to retinal cells or something like that, but essentially you have these sort of damped responses when you have a really big input signal. So your ear goes, well, that's too loud, it damps it down. But when it's very soft sound, you get a very sharp response. And so from an engineering 101, this is, it's maximizing signal to noise ratio. So you're filtering out all the noise, you're increasing the gain, and you're really trying to zero into the sound. Or you're like, this is overwhelming, so you're turning the dial down as much as you can. And this is happening sort of automatically all the time. And this is because of the nonlinear responses of your inner hair cells. So now these are actually results from a chip I made, and I always say that I made a great model of tinnitus because it was constantly ringing. But of course, that's the nonlinearities. In a way, it's sort of telling you that it works. But from making technology, it's not great to be always ringing. The other thing that nonlinearities give you is it gives you, in a hearing context, there's all these other kind of secondary effects. So I won't go into it because I've kind of rambled on a bit here, but there's this sort of phenomenon called two-tone suppression where when you have several tones, you get a different response at your inner hair cells because of the second tone. And you also have these odd-ordered distortion products. And all of these things give you the kind of richness of sound that you hear. But they also have other applications. So they probably are helping you doing localization with your hearing as well. And again, if you're not including these nonlinearities, then you're losing all of that extra information that you're gaining from having them there. And neurons as well, as I said before, they have this very broad suite of behavior that they can produce. And people that have measured from neurons obviously have seen these behaviors. And this is all because of their kind of, they're not linear things. So how do we deal with these, either in hardware or even computationally? We usually don't. Like sometimes we might make a sort of a piecewise linear representation, but they're usually too hard to deal with. And I'm just here to say that I think maybe we should deal with them because I think maybe a lot of the magic comes from having them there. Unfortunately, most of the time, and I'm not at all not guilty of this, but we basically use neurons as like little addition things. They're just little summers. But there's so much more than that. And so exploring how their nonlinear properties can improve computation is probably an interesting thing to start doing. So as I said, complexity is sort of, it's a big topic. And there's, if you try to get a definition of what complexity is, it's sort of difficult. So I won't even try to define it, just to say that I think we can all agree that the brain is complex. In fact, I'll go as far to say that a single neuron is complex. And, the fact that we're all trying to do something with it, we should all give ourselves a pat on the back because it's a hard problem. It's usually something we find in large systems, but as I said, like a single neuron is crazily complex from our point of view, not really understanding what it's trying to do. I can't recommend this paper enough. It came out a few years ago. It was called, Could a Neuroscientist Understand a Microprocessor? And so the paper is about going through, taking an old school microprocessor from like the 80s, so like really simple stuff, and putting it through neuroscience techniques to try to understand what it does, sort of try to reverse engineer it using the techniques that are used in neuroscience. It's a really interesting paper, and I'm not going to really go into too much about what it says, but one of the key sort of findings from this is that the techniques were really great at getting the structure of the data. So it was pretty clear what the structure was, but then the information processing part was completely lost. So it was good at structure, but not good at information. And so it kind of opens this enormous can of worms is, do we really understand how information is flowing around in the brain? Probably not, but these are kind of interesting thought experiments. How could we change things in sort of this simple example? How could things change in order to understand information processing better? And perhaps focusing more on information processing should be something that we should be doing as well. So the fact that the brain is so complex, and the fact that we're all very in love with our von Neumann computers with their fetch, execute, and what's the last thing? I can't remember. Anyway, our computers, the way they are, they're very structured, do this, do this, do this. This is what our neural networks look like. You know, they're inputs, hidden layers, outputs. There's no richness at all to this structure because we get this structure. This is not, you know, like weird to us. It makes sense. It's comfortable, you know. But the problem with doing networks like this and thinking about networks like this is that then from a let's make these guys work, we end up with these big matrices and lots of power consumption. I've got a slide later which says how much that is. And, you know, like for me, this is the slippery slope, you know, this is leading to the dark side. You know, we end up creating these networks that are just so basic. And we've actually created networks that look exactly like what our computers use. You know, like we're trying to be different, but yeah, anyway, you can throw tomatoes at me later. But yeah, essentially, machine learning at the moment is moving big matrices around. And of course, you know, we're not moving big matrices around in our brains. You know, if we look at one row of this matrix, we could abstract it to being a single neuron with some inputs and some weights and a beautifully drawn action potential here that possibly looks more like a hard one, but, you know, I didn't have much to work with here. So, and then we could say, you know, instead of solving a matrix, why don't we just update our weights based on whether the neuron fired or not? And then we could say, and if I fire, let's make sure no other neuron fires. And then I could use some sort of learning rule like STDP, right? So STDP being sort of Hebbian learning. So if the spike at the input comes before the spike at the output, then they must be sort of correlated somehow. But if it comes after, then they're not dancing together, so, you know, discount the weights there. And so essentially you can do the whole matrix that way, right? So you can do it iteratively with a bunch of neurons, never ever touching a matrix. I'm really not against matrices, they're just, you know, they have their place. So it becomes unsupervised and it becomes iterative. So instead of taking, you know, burning down rainforests to do a matrix multiplication, you kind of slowly and iteratively update your network as you go. And so this is just some data from a network that we made. So there's a data set, probably many people know it, called MNIST. It's like the baby data set of machine vision. Like it's like, you know, in the future, the future people, this is what they'll be getting the children to be programming in kindergarten. But it makes for a good visual example. So the MNIST average, so for people that don't know, I should say, because I've just sort of put MNIST down and I should probably tell you what it is. So it's handwritten digits from US zip codes. So they kind of standardize them into, I think, 24 by 24 pixels. And, so the whole task is, can you train a network to work out that that's 2 and that's 3? And, some of these people with their handwriting, honestly, postmen really deserve a, tip of the hat. But, most of the networks do pretty well with this. So I think humans do it about 98% accuracy on this. And I always think human performance is where we should be headed, because once you get over 90%, you've clearly overtrained the network. You shouldn't get kudos for that. You should be told you're wasting time. But anyway, that's rant. So if you take all of the digits in this data set and you kind of average them together, they kind of look like this guy here, which is a fuzzy 83 kind of thing. So we've been playing with these spike time unsupervised neural networks. They're stunning. And that's basically what I described before. So it's basically just little neurons that fire based on a sort of Hebbian learning type of thing. And, it doesn't look exactly like this, but it looks like a digity kind of thing if you average all of the features in that network. If you take, a deep network, it doesn't look like anything. Like, it's obviously learning the anomalies in each image rather than the actual features of numbers, which is super interesting. And so the neuron that I described before, that's your feature neuron. And so if you have a whole network, then these are, what those feature neurons average to. And then let's see if this works. I did try this before, but it's supposed to show something. Oh, there we go. So this is the network learning. So this is just a selection of 100 neurons in the stun network. And they kind of just all kind of self-organize and just learn various features of the input. So you can see here things that look kind of like 4s and 1s and 9s and 0s and 3s. And the deep network just looks like, well, you can't really see it very well, but it looks like weird box things that don't mean anything. And so, the matrix multiplication way using kind of the mathematical method gives completely unexplainable results, and the way which kind of copies in an extremely abstract way how the brain works gives you results that kind of make sense. And, no rainforest died in the making of this graph. So, it's a pretty interesting way to get around the complexity. The other thing is that I was going to show a video on this, but this video takes like thousands of years to run. So what we did was we made a montage of random MNIST digits, and then we got the trained networks and the inputs to the trained networks were like one image at a time offset by a pixel. So we just kept scanning across the image that way. So the deep network is always giving a response. So we've got a 5 and a 6 here, and when it's right in between those two, it still thinks it sees a number. There's obviously not a number there, but these things, they just give results even when there's nothing there. The stun network, the one that we use that we call BitNet, it only gives responses when it's on top of a number. So this is another thing. The deep networks, the ones that are apparently ruling the world, they're constantly giving results whether there's anything there or not. Whereas this kind of, elegant sort of semi-plausible network is only giving results when it sees something that, is something that might be something that it's seen before. So complexity is complex. And in the particular case with the stuns, actually, when we add the feedback, and in some sense it's a bit more complicated, it actually gives better results. and the feature neurons are more intuitive, and it actually reduces power consumption, and you don't need to tune lots of parameters. It sort of all works out that in the end. So I am not saying at all that these simple networks are the answers to everything. I'm just saying that perhaps this is something that we should look at, and that there's a lot of work to be done in the area, but it's pretty interesting, right? Like, there's a lot of people heading straight for machine learning is going to rule the world, and possibly it will, but maybe some of these techniques can improve things quite substantially. And then my last bee in the bonnet is power consumption. I'm sure you've all heard about how extremely power efficient your brain is. I try not to use it too often because, I'm trying to save power. But generally, it's 20 to 40 watts a day or something like that, which is, impressive. It's very light, it's squishy. It ticks a lot of boxes when you compare it with your mobile phone. The current computers we have, and I didn't even bother going to the biggest supercomputer. I used to do that, but, a single AI model can emit as much carbon as 5 cars in their lifetime. That's insane, right? Like, it just blows my mind how much power we use on computation. And this is a real problem. This is not some sort of, for many years I've been getting up and telling people about power consumption, and everyone's like, oh, it's power consumption. But really, it's a problem, we shouldn't be using this much power, especially when the results are so kind of dodgy. But anyway, so there is really need to keep power consumption down, just on all kinds of levels. And the solutions to this are, like the mantra of the neuromorphic community in the early days was that if we make it all neuromorphic, then, we're mimicking the body, so therefore we'll use less power. And so excuse me, certainly some sensors do use a lot less power, but the processing required on the outputs, like event-based sensors and things, they're quite computationally burdensome. It's kind of incorrect to say that these things are low power when, sure, the actual thing is low power, but then, you need a rack of high-powered FPGAs in order to process the data. The power consumption problem needs to be caught at every angle, and particularly processing data. How do we do it efficiently? I think the answer is in better algorithms. I think, we can't not go along with this sort of wave of AI, but perhaps if we improve our algorithms, we can reduce power. And of course, there's a whole heap of different technologies in terms of, we've been living in a silicon world for the last 50 years, and so there are new technologies coming around. It will take a long time for them to mature, and I don't know whether they will. And then, of course, we have to be aware of, are we modeling the right things? Are we modeling the structure of something, or are we modeling the information processing? And if we're going to really have, revolutionary algorithms, then we need to think about how the information is being processed as much as the structure, at least. That was my rant. In terms of what we've done, neuromorphic engineering has been around since the sort of mid to late 80s. So what's that, like 40 years? So in that time, there has been some neuromorphic products that have come around. Part of it is, I used to have this thing in my talks where I talked about something called Moore's Law, which was this idea of integrated circuits getting better every 18 months. And I think the current node at the moment is something stupid like 2 nanometers or something like that. It's insane. Like, you just can't imagine these crazy technologies. But, it does keep getting better. Like, even if we stop at 2 nanometers, there will keep being improvements in silicon. So the neuromorphic promise of improving that never eventuated because we never reached the ceiling. Now, we probably will, but it's still cheaper to make silicon chips. So perhaps the right way to think about it is, how do we do better algorithms and better structures on those chips in order to make them improve their computational performance? And this area has attracted a lot of interest from the big companies as well. I think a lot of it is because of, it's cool to say, I'm using neuroscience to make a better processor, because most of these things are like hammers without nails. They're completely useless. They're not serving a purpose in terms of, making computation easier, and most of them are just becoming, matrix multipliers, that might use slightly less power, but, it depends. So there's, if we're going to move forward, then we probably need to look at not doing these structural chips that kind of look like feed-forward networks, but actually thinking about what are some of the techniques, what are some of the algorithms that can actually improve our technology. All right, so just because lots of people have been asking me about this, probably more than anything else. Nobody noticed my hair. No, I'm just kidding. I didn't do anything with my hair. So why did I leave academia? For all the international people here, it's weird to leave academia in Australia because there's not that much opportunities for people with PhDs. Usually that's a sort of negative on your resume, like you hide it at the bottom. I didn't waste 4 years of my life. But I think that's all changing. So for all the young people in the room, there's plenty of opportunities for people with PhDs who may be completely freaked out by the idea of being an academic. So why did I do it? I mean, everyone says this, it's just bureaucratic nightmare. I found that I was the sort of administrative assistant to my postdoc, so I was, constantly, filling out forms and doing budgets, and I'm really bad at that stuff. Like, some people are good at it, I'm terrible, so I think, I spent a whole day once looking for 1 cent, a whole day. It's just, you can ask me about it later, but that was the straw that broke the camel's back. I kind of came home that day, I'm just like, I can't do this anymore. The other thing is funding. There's this weird thing where when you hit associate professor, people started calling me junior and inexperienced to lead a team. Now, people that know me maybe think I'm a little bit nutty to lead a team, and I would accept nutty, but I wouldn't think that inexperienced would be the right word to describe me. So it was very, what's the word? It felt like I was kind of wasting my time, like it was a ceiling that I couldn't break through. And it was a perception thing, I'm not sure, but it was, you do so much work on these grants and then you get a stupid comment like that and it's just like, why do I bother? But it's easy to get applied research funding, generally, given what I do. But this then comes with another problem. I can't really hire PhD students on year-to-year contracts. I can't ask someone to come and join me on a project that may or may not be, funded the next year. So then, you end up with lots of research assistants, and it just becomes, it's hard to build a lab and a team out of that. And the other problem was just coming back from maternity leave. It was really tough. I didn't actually expect it. I probably was naive, but there is a perception that you're not taking work seriously anymore. And it's weird, but lots of female mentors were trying to tell me that, I just had to feel guilty all the time or something, but I don't know what the answer with that is, and I know that that's not the experience of all women, but it was just a little odd that I kind of came back and I really felt like I had to start again. And I don't think that that's how it should be, but I have no solutions, absolutely none. I cannot offer you any. I kind of felt a little bit guilty about leaving academia. I felt like, I should stay and do this, but, other things happened. But when I was making this slide, I was looking around, and some research at the University of Newcastle sort of showed this retention rate problem for women in STEM. I kind of felt a bit better then, because I thought, well, I'm not the only one. I'm a data point, and there's a lot of us. But, like when women get senior, it's just like, they're just like, oh, I'm not doing this anymore. Again, absolutely no solutions. I offer you none. Just to say that it is a problem, and I don't know how to fix it, and I'm not gonna fix it because I've left. But I do think that maybe this is something with people who are in power, probably nobody here, but if you know someone that that maybe you can have a chat to them and tell them that how to fix this. I really don't know. I think one of the encouraging things is that there's a lot of support for young female academics, but somehow that becomes an extremely large slippery slide at some point. But it's not all doom and gloom, right? Like it's not like I became unemployed or it completely broke me and I'm sort of cradling myself. I had a great academic career. I really enjoyed it, and I hope to remain connected with it. It's just that there was just other things on the horizon that came up. So, what's it like on the outside? So I feel like I'm a civilian now. I don't even have an affiliation. It's very cool. So the difference is that I have to do something particular. I'm not like, this is interesting, and constantly going down rabbit holes. I mean, if we're going to be completely honest, my academic career got broken because I got too interested in too many things, and I couldn't keep up with it. It's like an octopus. So this sort of focused me on, like, do this. Things actually have to work. I know this sounds really bad, but I'm sure you all know, right? Like, you get something for a paper, and it was like the one time it worked, and you took the data and like, it works. And you know that if I fix this and if I did that again, then totally it would definitely work. But you show the good parts in your papers, like these are the good things that happen. The number of times I've tried to copy someone else's paper and get their results and didn't get them, I'm like, oh, so that's what happened. But in industry, you actually have to make it work properly. People actually care about that sort of thing. I have bosses, and I need to tell them how things are working. It's a very strange phenomenon. I like bosses. I think I needed a boss for my whole life, because otherwise I just go off on weird tangents, as you can tell from my talk. There's still grants and things. There's quite a lot now in Australia. There's a lot of interest in technology and that sort of thing. But it's actual real money. It's not like scrapping for $300,000 and the university takes 50% of that, and then you're like, who can I hire for $150,000? It's not that bad. Nobody's like, oh, well, she's too inexperienced. They're more interested in actually what it is you're trying to do. But there's no kind of personalization in these grants, so it's actually quite nice. I don't have any administrative burden. I am going to make fun of all of you and your administrative burdens. I have none. I have a person, and she takes care of all of that. It's wonderful. You should have one. And no, you can't have mine. So the similarities are that I still get to work with amazing scientists and engineers. So I poached them all out of UTS with me, and we have our nice little fun team, and it's heaps of fun. Probably they're all super nerds, so they'll probably end up doing PhDs at some point, but this is a nice little diversion in their lives while they're on their way to their, nerdy futures. This is not everywhere. I'm not going to pretend that this is every outside of academia. Where I work is extremely flexible, so we don't do timesheets or hours or anything like that. We have one meeting a week, and that's just to, catch up on gossip. And usually people have to mute me because I go off on tangents. But it's extremely flexible, and I don't feel any different. Like, the best thing of academia was that I could just, kind of wake up and spend a whole day thinking, and I can still do that now, except I'm not dodging administration. I actually am thinking. And we get to do research. So we're still doing research, and we're still researching pretty interesting questions. We're just doing it in a targeted way. But, I'm excited about having left, so probably you need to ask me in 12 months when I'm completely like, this is a nightmare, and applying desperately to all of your universities for jobs. So yeah, ask me then. So we're at work. So we're doing at-the-edge technology. Really, we're just, having fun, experimenting. We've got one product that we're playing with, but generally we're just trying to make sort of at-the-edge learning and sensors better using, a lot of the kind of neuromorphic techniques that I discussed today. And a lot of the things I discussed today are things that we're kind of trying to play with. So the stuns are something that we're quite interested in, because reducing power and just speed of performance and robustness is just really critical to us. We really want to work with universities. We already do. So, if you're okay with this, come and talk to me. We're super interested in, everything at the moment. And yeah, we're keen to collaborate because, we know that it's tough getting research funding these days. There's a team of thousands who have contributed to this talk in one way or another. I tip my hat to all of them. And I tip my hat to you for listening. Thank you.
All right. Wow. That's basically what I wanted to say. This may have been actually the most consequential presentation at this whole meeting, in my point of view. This is exactly the problems we're dealing with on this side of the aisle. And I was almost late for this talk today. I thought this was, we have many talks, right? And now I'm stunned because the problems you mentioned, you just nailed it. Over and over and over again. These are exactly the problems we're dealing with, we're afraid to face, oftentimes, and yet we need to face them. And in this organization as well, I think we need to kind of start thinking about how to openly confront these incredibly deep, annoying, mathematically annoying issues. And so I was sitting, and I was honestly, now I am going on a rant, but I had to say it. I was sitting and listening and thinking, gosh, Tara may be the only one who's not on anything in this room. Everyone else is, all of us are doing something, and we have our approaches, and we love them. They're consistent, they're self-consistent, they're lovely, beautiful little niches, and all of it. But we need to face it. And from that point of view, again, thank you so much. Maybe it didn't flow perfectly at times, but I think you said what had to be said. Thank you.
Thanks.
Please don't hesitate to come down and just ask questions here at any of the microphones. Do you want to say a little bit about sort of the funding environment for things like startups, like yep. Particularly the one that you're involved in, because that's also been, particularly in Australia, a really big issue as to how we actually get funding for these sort of ventures.
Yeah, so I didn't talk about this, but I'm a founder of a different company that I'm not working for because of that reason. It's so hard to get funding. So we got funded for a couple of junior engineers, and the rest of us are just sort of playing in our spare time because it's really hard. And there's this there's this sort of choice that you have to make. Do you take investment that if your thing becomes big, then you're going to give away 90% of your company, basically? Or do you kind of hunker down and try to do it in your spare time so that you kind of keep ownership, or try to find a few angels? Everything, so my actual, the one that I'm a founder of, that one we're just self-funding, and we've got some small industry grants for it. The one I'm at the moment is privately owned by people who made a lot of money on a different startup. So that one is again sort of privately held and doesn't have any investment. It's something that I've looked into a lot and had many long conversations over how to do it. And at the moment, as I said, there's really just the accept money and accept the fact that you're going to lose a lot of what you're doing, or work really hard in the off hours to try to make it work. And it could be so much better. And it's really annoying when you see government funding for $100,000 or something, which is good if you're just starting out, but then they're asking for 50% matching, and you've got to where am I going to scrounge up 50 grand from, sort of thing. So it's actually a really, that's why I don't work at my own startup, because I ended up consulting to the company that I'm working for now through my startup in order to get enough money so that we could keep it alive. It was just weird. It's not an easy environment, and if you're looking to take off the shackles of bureaucracy, then don't do your own startup, because you've got to be doing everything, writing the grants, doing the books, there's no money to have someone to help you. So unless you're really into that sort of thing, then it's actually a really tough road. Yeah.
Thank you very much for the talk. I really appreciate the problem that you state. So I just have a specific question. So for the standard network that you create, does it work in other tasks like this? The example you show is on imaging, right? Does it work on language or other tasks? And what's the feature that make it better for that task?
So it actually probably works better with language. So we're doing text generation at the moment, and it works pretty well with that. The reason why we do the MNIST example is just that it's visually, I could show you weird vocabularies that we've created with the network, but it's not as interesting. I mean, actually, because it's because you encode whatever it is temporally. So in terms of image processing, you need to temporally encode each pixel. It's actually an easier task to deal with sound or text, because that's data that actually moves temporally. So it actually is more suitable. Whereas there's, here I am being dishonest here with my power consumption thing. There's this whole step where you have to take the image and you have to convert it into timed spikes. Which is, not overly burdensome, but I guess when you're at 4K pictures, it becomes somewhat burdensome. One feels like perhaps an imager that has outputs in time rather than in space would be better. But so it works probably better with text or sound.
And the other question is, so you said your startup is currently try to keep it working. So do you have some idea how long it takes to when a startup until it's permanent and can make profit? And
yeah, that's a good question. I feel like it's how long is a piece of string. A lot of it is luck, right? So if you know someone who knows someone who has a contract on something that you could fulfill, then you can get a small door open to getting funding, and if you make the most of that, then you can probably make something out of it. But it's very precarious, right? So most startups fail. And, I will be completely happy to fail because, at least I tried. Maybe not hard enough, but yeah, I guess part of the whole thing is just bumping into the right people. So to be successful at startups, I think you need to be going to a lot of events, talking to lots of people, and trying to make the right connections, because the difference between success and not success is probably someone you bumped into at some startup thing. It's very it's very random what succeeds and what fails, I think. Yeah.
Thank you.
Perhaps I can just follow up with a question about intellectual property, and two parts to that. First of all, to what extent does the startups that you've been involved in actually depend upon some core of intellectual property that you actually have exclusive control over, and therefore have some sort of niche that you could actually address that others can't?
Yep.
And then I guess following on from that, in the particular area in which you're working, like particularly spiking neural networks, to what extent do you think we're actually at the start of a new phase of actually thinking about the way in which we do computing?
Yeah, so in terms of IP, it's like God. It's everything, right? So, just last month I was breaking my back just getting a patent done because it was very important to have the patent finished in time, and that sort of then makes us all relax a little bit because we actually, because you're constantly thinking someone else is going to do your thing, because everyone is kind of working on the same problems, and even if they don't solve it the same way, like you kind of need to have IP so that you can at least have something. You can say that, so when you're getting funded or doing a contract, you can say that we have rights over this technology, so we can use it, and you can pay for a product from us, and there won't be any big high court appearances. So for the two that I'm working at, IP is sort of everything, because we're not getting outside funding. We do rely on IP, and so we're very, very hard at work generating that IP. And to be clear, the IP isn't, like for us, the IP isn't about algorithms and things, because, well, it's hard to patent an algorithm, and I can dig up a paper from 1960 that came up with the same thing, because, it's very circular science. Somebody's always come up with it. It's very frustrating. But for us, it's about how we implement. So we're more about hardware and how we build something rather than what it is that we're doing. In terms of spiking networks, I'm still kind of on the fence, partially because of the whole you need to change things into spikes, and that is an overhead that's basically an A to D converter type problem where you definitely need that. So then that adds, power and latency to the whole processing chain. That, this is what happens when you start to think in systems rather than just individual parts of the system. Unless the output's coming to you in spikes, then you're adding to the problem. But in terms of unsupervised learning, it's really very elegant. The fact that you can learn MNIST, and the results on MNIST were, slightly better than the deep networks. And so, we were kind of learning at an almost human level with very simple network, pretty small. And, the devil is always in the details. MNIST is a toy. So we can kick around the toy and we can do the toy, but when you're driving in a car at 90 kilometers an hour and a kangaroo jumps out, that's when your network is being tested. It's not doing MNIST. So I think there's value in exploring it. I think it has some inherent properties that allow it to have, I don't think training networks will get us to the point of autonomy that everybody wants to get to. You need networks that can learn on the fly. and be able to do that in a way that you can see how they learned so that you can sort of, forensically deconstruct, if anything goes wrong. At the moment, nobody knows. People just, I'm changing the learning rate, I'm changing this parameter, like, who knows? I think there's a really nice property that you can actually see how they're learning, and I think that's, if nothing else, that's super beneficial.
Hi, it's interesting talk. I want to ask about the information processing.
Yep.
So I want to ask, what's your perspective? Like, how are you defining information processing in your framework? And how are you dealing with it?
Yeah, well, I guess the short answer is I'm not. I think of it like a thought experiment, right? So I'm standing here and I'm looking at you and I'm having thoughts and there's a noise over there. If I just look at the data, I'm just seeing spikes. I'm going, ooh, there's a spike train, and that's nice. And, but it's being collected somehow in a way that gives me all this information. And looking at individual spike trains or just focusing on my vision or my hearing, it doesn't cut it. It's not giving me the picture. But, it's so hard because, how do you dissect, how do you pull things out and understand them when clearly what I'm hearing is affecting what I'm seeing? And, I'm feeling a little hungry right now. And I'm like, that's kind of on my mind too. And so there's all this stuff going on. And somehow there's some sieve in my head that's filtering out which are the important things that I need to deal with right now, including continuing making words. And so, maybe it's looking at a higher level instead of looking at individual spikes and how they're coming out of different senses and going into different brain parts. Maybe it's about, collectively, doing some sort of systems engineering approach or systems analysis approach to what's going on. I really don't know. The problem is I promise no solutions. I think I've mentioned that many times. But yeah, I think it's looking at, because we try to confine the problem so much. We put the rats in the cheese mat, and so we think in the rats just thinking about cheese. And so when we're measuring the rats, then that's the only signal that we're getting. The rats could also be like, well, rat B just called me a name and I'm not happy about it. Or, maybe he didn't have a good sleep that night and he's thinking about that. How do you tease it all apart? We can try to confine our experiments more and more so that we get to something, but then are we losing the richness of the information then? I don't know.
Maybe I will catch you outside or something.
Okay, thanks.
Good. Well, thank you very much, Tara. It's been a really fascinating talk.
Thank you.
We will finish up there because we have morning tea starting shortly, but let's thank Tara for a fascinating, wonderful talk.
Thank you.
Just very quickly before everyone goes, there were a number of people who didn't pick up their T-shirts from the, I think, who actually paid for them as part of your registration. And so if you haven't actually picked them up yet, please make sure that you do that sometime today, preferably either this morning or over lunchtime. So don't forget your T-shirts if you've paid for them as part of your registration. Or if you'd still like to actually get them now. We did actually produce a little more than were required, and so there's still some additional T-shirts there as well.